Okay, so let me start from some introduction. So when we speak about some random operators on random matrices, the key physical parameter which we're usually interested in is the localization length of the eigenvector, which means the typical length scale of the eigenvector. So localized eigenvectors usually correspond to lack of transport, and so Poisson local spectral statistics. Usually it appears in low dimension or when we have a strong disorder. And delocalization means that all elements of eigenvector are more or less the same, and it corresponds to the diffusion in solid electric conductors and GUE local statistic, which means the statistic of local the local statistic are the same as the statistic of eigenvalues of matrix, Hermitian matrices, not especially Hermitian, can be also orthogonal or some matrix which has independent Gaussian elements and some class of symmetry. So usually this GUE local statistic comes from random matrix, and delocalization and diffusion comes from random operators, somehow like this. So from the random matrix point of view, the main interesting question in the connected to delocalization is the behavior of the correlation function. So we consider the usual correlation function, and there is a conjecture of which due to Wigner and Dyson in early 60s, there's the behavior of this, the local behavior of the correlation function depend only on the symmetry type of the matrix. It does not depend on elements distribution. So more precisely, if we want to formulate the conjecture for Hermitian case in delocalized regime, this means that after proper normalization, the limit of the correlation function, if we put all parameters, it doesn't work. Probably it. All parameters in 1 over n neighborhood of some point lambda 0 inside of the spectrum, then when we take the limit is the same as we obtain if we put here just usual Gaussian unitary ensemble, so matrix with independent Gaussian elements. If we take here if this matrix is Hermitian, if we take the real symmetric matrix, we obtain different limit, but this limit again the same for all symmetric matrices. In general, there are more classes of universality, so it's not completely fair to say that we have only 3 classes, but the main point that everything determined only by the symmetry type of matrix, not by the distribution of the elements. And so if we have behavior like this corresponds to delocalized states. If we have that correlation function is factorized, it corresponds to Poisson statistic and so to localized regime. So in general, so the question about order of localization lengths and the question about universality of correlation functions, they are closely related but not the same. Roughly speaking, we can't prove one of them from another, but usually we have to do the same to prove both of them. Okay, so from the one side, for the most common random matrices, which is Wigner matrices, so again Hermitian matrix with independent but not necessarily Gaussian element, beta ensembles, which corresponds to beta log S, and the sample covariance matrices, and so on. We have, so for most common classical random matrix ensemble, we have delocalization, and so we have GUE or GOE, local spectral statistics. And from the other side, we have Anderson model, which is probably one of the most challenging for mathematical physics for long period of time, but this is in higher dimension. In dimension 1, it looks like this. So we have random potential on the diagonal and Laplacian on the off-diagonal element. So in principle, we can consider this like a random matrix because we have some randomness, but of course, here we have randomness only on the diagonal part, and also we have non-random part. But it's known from the work of Ehrlich, Spencer, Eisman, Molchanov, and other people that in dimensional 1, we have here the complete localization and Poisson local spectral statistic. So one can see that we have, so this is example of two different regimes. The band matrices are natural intermediate model between these two models because it interpolates between Wigner matrices and random Schrodinger. And interesting thing about the band matrices is this also has some spatial structure, but technically it's much more accessible than the random Schrodinger operator. So what is the random band matrices? In general, we can take some box lambda on lattice, and we consider Hermitian matrix, which elements parameterized by the indices on this box, and we assume that elements are independent, but now not identically distributed. So the mean of all elements we put 0, but the variance now is not equal to the whole elements and is given by some function j. So here you can see that if this j usually take like an even function, and usually it has compact support on 0, 1, for example, or rapid decay if you want to consider. So if you can see here that since if j has a support 0 segment 0, 1, then if j minus k bigger than w, the covariance is 0, and if j minus k is smaller, it's of order 1 over w in the d power. So this, in 1D case, this means that our matrix looks like this. So you have n times m matrix, and you have a strip of y2w with non-zero covariance, and here covariance is 0 or has a rapid decay. So the main parameter here is the band yw, and you can see that varying w we can obtain one diagonal matrix which similar to the random Schrodinger operator, and if w is of order n, we obtain usual Wigner matrices. Yeah?
In which way does the dimension matter for the band matrices?
So we can, this means that we compute the distance between two elements, j and k. This distance computed in some dimension. So in 1D we have only two neighbors, for example.
No, but for the random band matrices, if you make the bandwidth very large, is D still an important parameter? Still important?
No, if D is of order n, no, it's not important. Certainly we have the same.
I think your question is if you see here
it depends on what large. Yes. So let me describe the.
Width, and then there's a dimension. And
yes. It's the. So let me describe. So why is this model is interesting? Because this can model the Anderson metal-insulator transition even in 1D case, and so we can vary in W. We can see. So the conjecture is the following. This is a physical conjecture which was obtained in 1931, probably for 1D. It's a conjecture of Mirlin Fedorov. And so the conjecture is the following. So that in D equal 1, localization length is W square, which means that if W grows faster than square root of n, we obtain delocalized regime and GV statistics. If W grows slower than square root of n, we obtain localized regime and Poisson statistic. For D equal 1, the expected value of L is e to the W square, which means that if, again, W grows faster than square root of logarithm, we have delocalization. For W slower than square root of, and we have localization. And in dimensional higher than 3, we expect that we obtain delocalization if only W bigger than some W small. This conjecture is in correspondence.
I wasn't clear about the answer to the previous question. No, where does this L going like W squared come from?
This is conjectures. They come from some physical calculation, so I'm going probably.
That's for a real Anderson model, not for the random matrices.
This is conjecture for random band matrices. Yes.
But what is it P equals 1?
Okay, when she writes a matrix like this, I know it's a little confusing. I had to answer this question.
This is D equal 1, this matrix.
Yes.
So usually the vertices are just.
This is for D equal 1. So, but for higher D, I can't draw such a picture. Yes, but in general, you can.
It's a two-dimensional set, right? So it would be a very sparse kind of funny-looking matrix.
Yeah, so you can see that here JK on lattice. So if in 2D, you roughly speaking, your band is. So probably you can imagine the 3D matrix or something like this with elements, but yeah, but probably it's better to keep in mind this picture and assume that in 2D on 3D, just we have the definition that if we number the elements by some elements of lambda, and if j and k far from each other, then it is 0, and if they of the distances of size w or smaller, then we have some constant dispersion, something like this. Okay, and this conjecture really is in some correspondence for conjecture or Anderson model if you put the strength of disorder lambda of order 1 over w. So you can reformulate this conjecture from the conjecture for Anderson model. But in general, band matrices looks much more accessible than Anderson. Okay, so this is a conjecture, what we know really. So. For D equal 1, yes. For D equal 2, I'm not sure. Probably it was formulated a little bit later than. I don't remember the proper citation, but.
So the conjecture, the enormous is not important.
The what?
Randomness is, we can assume that as smooth as possible.
You probably don't even know for standard IID, right?
Standard IDs, you mean the Bernoulli's IDs or what?
No,
what is it?
standard Gaussian.
Yeah, we don't know it.
Yeah.
Yes,
Yeah,
yes.
But the conjecture for more general data.
They are physicists, they don't really consider such kind of conjecture. The question. Oh, I think that you have, yeah, not, but definitely you have to obtain the second moment set 2 plus epsilon, but I'm not sure that you need something more. Yeah, but I'm not sure.
I mean, usually assume Gaussian. These problems are already open for Gaussian. So.
Yeah, Gaussian or sub-exponential tails if you want to, so it's depends on what you. Okay, so now let me formulate what we really know about cells. At present time, not such a many results about this case, even for D equal 1. So we know we have the result of Schenker of 2009 that localization length is smaller than W in the 8th power, which was proved by the technique which comes from the random Schrodinger. It's now people expect that we have improved some houses bounds by the same methods, but in general we still can't remember that in 1D the expected value is W square, so we're still very, very far from W square here. And yes, yes, this is for 1D.
Just remind, localization length meaning where the eigenfunctions is supported?
Yes, roughly speaking, yes. So from the other side, it was proved for Wigner matrices, so for W equal n in the work of Erdős-Jaulin, that localization length is bigger than W, and this was proved by standard random matrix methods, which comes from all this business with universality for Wigner matrices, sample covariance matrices, and so on. And this the result about localization length, and the result about the universality was obtained very recently. It's just a couple of weeks ago. Was appear in an archive that they can prove gap universality for W of order n with zeros here. So this W is of order n.
What does it mean?
Gap universality means that if you consider difference between so you have some eigenvalues, you take the indexes of eigenvalues which lies not too close to the ends or to the beginning, then you write something like these gaps, normalize it properly. I don't remember, probably it's n times rho of energy, something like this. And you take some test function phi, consider this for e plus 1 e plus k. Consider this and take the expectation of this for the band case minus the expectation for GUE case. And you can prove that this is small, with the expectation is small, and with, I don't remember what is the constant of the case, so probably this expectation minus GUE expectation, this for fixed k and I inside of the spectrum, this bounded by some power of W minus something like this with some constants which depend only on test function phi that you have here.
So it just says that the differences of
yes, the distribution of the difference is the same as for GUE case, roughly speaking, something like this. So this is a little bit less than general universality for correlation function, but usually physically it's more interesting question.
So what is K?
K here is some fixed number.
She doesn't want just the nearest neighbor,
So you don't
next
count
one.
Yes, you take the I inside this K and take some few of nearest neighbors there.
Some few near it. I couldn't really quite read what you had.
Doesn't matter. The
Yes.
spacing, just the nearest neighbor.
Just the
You
nearest
don't confuse them.
Okay, yes, but in general,
Nearest neighbor.
okay, yes,
Then
you can take
W
the
equals n means there's no corners, right? It means
Well, it's
Wigner, no?
it could be
Wigner.
small constant times n. So
Yeah, okay, half n.
Half that, 1/3 end, yeah.
Okay.
okay. There are some other. So this is only the result about the few modes. General band matrices like this. So by the development, this approach of Erdős and some other people, we can obtain some other results that also obtain some bounds on localization length, but this is not the localization length in a strong sense. So this means that it was proved that estimates of delocalization, so delocalization holds for most eigenfunctions only. So not for all eigenfunctions, just for some of them. But of course, the part of them is quite big. And there it was proved that first that L bigger than W in 7/6, and then 5/4, and the last result is even not uniform in volume, so it's even less than first result. So, and still, I just want to recall that we want W square, so it's still very, very far from what we really want to obtain. And what is the main problem of this technique? The main problem is that both to prove delocalization or localization, or to obtain something about the correlation function, universality of correlation function, you have to control the resolvent of your operator up to the imaginary part of Z of order 1/n. this is always the main point, what you have to obtain here. More precisely, this means that you have to control the expectation of Green's function square for this kind of imaginary parts. And the technique which was developed for first, probably for Wigner matrices, allows you to obtain control only for imaginary part of order 1 over W. And now it seems that this barrier is cannot be broken, so we don't really know how to break them. And if W for the square root of n, then of course the difference is quite big. So the estimates here, why they hold for the most eigenfunction only, is again because people can only control this 1 over W, not 1 over n. So now the only really technique which allows to control the resolvent on that size of imaginary part of 1 over n is the supersymmetry approach. And this approach based on the representation of the determinant as an integral of over the Grassmann variables. So the method is widely used in physics, and the most important thing that it's successfully used. But so potentially it is very powerful, but unfortunately the rigorous control of the integrals which one can obtain from this method is quite difficult, and usually the mathematicians don't really know how to do it in proper way. So there is a huge formalism how physicists work with this, but the most beautiful probably part and the most important part of this formalism is still lack of the rigorous basis. We don't know how to do it rigorously.
Just give the wrong answer. That's one other problem.
Yes, and we don't understand in what case it gives a right answer and in what cases it gives the wrong one. This is the main point. But part of this formalism is rigorous and can be used. So what we can do with this part of this formalism that we can use here. So probably I have to mention that the method has some restrictions, certainly. The main restriction that now, up to this moment, it's mainly applied to the Gaussian case. But in the case of band matrices, we don't have result even for Gaussian case, so even this is good. And there is a single case when you can apply this method for some when it was really rigorous applied to some non-Gaussian matrices, and this case of characteristic polynomials. I will discuss it a little bit later. Here, for characteristic polynomials, you can consider non-Gaussian distribution. But if we speak about the full model, so the density of states or correlation functions, the all results that we have now is Gaussian. And another restriction, and probably not the restriction about the supersymmetry, it's a restriction about our ability to analyze the integrals that we obtain, and that more useful to have some special covariance, not general J, but some special case of J's. And I'm going to consider here in this talk 2 cases. First of them is, I call it random band matrices. We have the specific covariance like this, so it's minus Laplacian plus 1 inverse, and delta is a discrete Laplacian with Neumann boundary conditions. You can see that in d equal 1 we have that J decay like this, and so if difference between I and J bigger than W, we have exponential decay, so this really can be considered as height of the band. Another model which we are going to consider is the so-called Gauge-Invariant Wigner model, and this is, you can read the general definition for any dimension, but in 1D this means the following. Now we consider matrix which consists of blocks W times W, and the covariance is each block is fixed. So here the covariance, this matrix is still Hermitian, the covariance can vary from block to block, but in each block the covariance is some number, which determined by, again, some function J, which is here I'll take like this. So this means that covariance here will be 1 minus alpha over W. Here is alpha over W, alpha over W, to alpha over W, alpha over W, alpha over W, and so on. So roughly speaking, we have our matrix is a 3-diagonal block matrix, something like this. This is, of course, this is still again picture in 1D case. In higher dimension, you have to be a little bit more careful with definition, but the main idea is the same. So now each side on your lattice corresponds to a block of size W times W, and so the dimension of your matrix is the number of elements in your lattice times W, which what you have. So density of states for both modules is known.
Excuse me.
Yeah.
Very difficult to read. Diagonals are the same or they grow?
This is the same because of boundary condition.
Sorry?
They are the same. This is just because boundary condition.
boundary.
Yes. As I told, the density.
I'm sorry,
Yeah.
I actually didn't understand the definition. Could you go back? So take this matrix and the entries are what?
So the entries are Gaussian elements, and so this, for example, this block is GOE matrix with covariance 1 minus alpha over W. This element has independent Gaussian elements which with covariance alpha over W.
What is covariance?
Covariance is just the expectation of square. Mean is 0.
I mean the second moment.
Yeah, the second moment, yeah.
Okay, look in there.
Okay. Okay,
so
yeah.
you take a different blocks.
In blocks,
and
yes, but in each block it's the same.
Okay.
Inside the block it's the same.
And then outside these three guys, it's zero.
Yeah.
Okay.
You can see that this model can be rotated by product of unitary matrix in each blocks, and that's why it's called Gauge-Invariant here. So you have invariance in, you can take unitary matrix like this and rotate all this by and obtain the same distribution.
Is this simpler than band
No, for the band matrix this is not true.
Yeah,
But
I'm saying,
here,
is this a simpler model than band?
No, probably yes. Probably the answer to the question is yes. But in general, it's more or less the same because physically you have something very similar here. So you have here also the band of the light 2W. So they have very, if we speak about this quantity like localization lengths and so on, it's very similar. But this is, for some reason, it's more. So it depends on in what way you want to apply the supersymmetry technique. For some question, it's more nice to apply this one. For some question, for this one. For some questions, it's more convenient to apply it for this one. So it's just rudiment of the technique. It's not nothing else. Okay, so the density of states for both modules is well known. It's semicircular wall, so the same as you obtain for Wigner matrices. And it was proved by Molchanov, Harunji Pastor for the band matrices in 1992, as far as I remember. But this is for this kind of models the same. So another object which I want to introduce here and which is also interested is the correlation function of characteristic polynomials. So this object is of independent interest because it has lots of connection, for example, with number theory and so on, but we want to consider it because of some other reasons. The first reason that although in general this object is non-local, because of course it has a products of all eigenvalues, so it's not local, but it's also expected after some proper normalization, it's also expected to be universal in some sense, which means that for example, for local eigenvalues for 1D random band matrices, we expect the same crossover. So we want to consider again lambda in the 1 over n neighborhood of some energy E inside of the spectrum, and we expect it to have the same point of the crossover for characteristic polynomial, that's for a real correlation function. So for w bigger than square root of n, we expect it to have the GUE behavior, and for w slow, which goes slower than square root of n, we expect to have some different behavior. And this object is much simpler than a real correlation function. Probably I have to say that for many kind of models of random matrices like Wigner, sample covariance, now sparse matrices, characteristic polynomials of this second correlation function was studied by supersymmetry, and even for not Gaussian distribution, so for any distribution which has a lot, probably if you consider the determinant, you certainly have to have lots of moments, because in other cases mean value is growth, so you have to have 2n moments probably, or something like this. Okay, so we know that for Wigner case, for sample covariance case, for beta ensembles, and for sparse matrices in some regimes, certainly this correlation function of characteristic polynomial after proper normalization behave like this function for GUE case up to some constant, multiplicative constant, which depend only on some, for Wigner and sample covariance matrices, it depends only on the fourth moment of the distribution. For beta ensembles, it depends on the first derivative in the energy of potential in the energy. So, but in general, the behavior is almost the same up to multiplicative constant. That's what we know. So we expected in the band case that we have, again, for w bigger than square root of n, we have GUE statistics, so the sign kernel, and for w smaller than square root, we expect to have 1. Okay, so let me formulate another reason why it's so interesting to study characteristic polynomials. The deal is that with to prove the universality, as I told previously, we have to consider the square, absolute value square of the Green's function for epsilon of order 1 over n. So you can see that this is the same as the second derivative of 2 determinant in the numerator, 2 determinant in the denominator, and this is just the identity. So the idea to apply why we want to apply the supersymmetry is to write the integral representation for each of these determinants. The determinants in denominator can be represented as a Gaussian integral. For the determinant in numerator, we use the Grassmann integral. So for the supersymmetrical point of view, this determinant in the numerator is like a first step in studying the full model. So we have this is so-called fermion-fermion sector, and usually if you can't study it, you can't study anything. So it's just a first step what we can do here. Okay, so now we have 4 objects. This object is characteristic polynomials, density, correlation function, and localization length. Yeah.
So you look at the characteristic polynomials at lambda, which are separated by distances of order of the spectral gaps, right?
Yes, certainly, yes.
So
in the
there's
work.
some general preparatory theory which says that the universality for these functions is more or less equivalent to universality.
As far as I know, no, we don't understand this completely. So we expect to have this, but I'm not even sure that this is true for all cases. So I expect to have this, but as far as I know, there's no theory that explains this in a good way. Okay, so let me formulate now what we can obtain with supersymmetry for all these 4 quantities that we have here. So first result is the results of characteristic polynomials. So if we normalize out second correlation function, so second correlation function, let me remind, is just expectation of 2 determinants. We normalize it by a proper way, and then the theorem is the following, that the limit if n tends to infinity of this correlation function, if we take this energy plus xi and minus xi, is sign kernel if w bigger than n to the power 1 over 2 plus theta, and is 1 when W is big but smaller than n divided by logarithmic and divided by some constant. So you can see that it's almost 1/2 that we have here. So on the level of characteristic polynomial, we really can see the crossover and the order of W of order square root of n. And certainly we have some gap between two of them. So we have n 1/2 plus theta and divided by logarithmic. So, but the critical regime is harder to study here.
Arbitrarily small.
Yes, that is arbitrarily
small,
small but fixed. Yes. And actually, I have some ideas how to work even in the critical regime for characteristic polynomial, but let's now.
You'll get a different answer at the critical regime.
Yes, yes.
And do you know what that should be or not?
There should be some set of function, as yes, I expect to have them. So I can't really prove it, but I can just compute something to see them. So I can see this set of function, but I don't know how to do it in a proper way.
And let me just point out, which may be obvious to everybody, but this is the same thing that you would get if you did it for GUE, right?
Yes, yes, yes. So first part means that if you take GUE or Wigner matrices, you obtain the sign kernel. So this is directly what we want to obtain for the real correlation function, but we can't obtain it for real correlation function, but here we really can do this. And so the first part was proved in 2013, and this was done by direct saddle point analysis. The case of orthogonal symmetry is also done. So it's I am going to speak about only unitary symmetry, but in general, in principle, you can, with more effort, do everything for orthogonal symmetry too. So for second correlation function, there's not such a big difference between orthogonal symmetry and unitary symmetry. If you want to consider the higher correlation, so then there will be some differences. This is because, for people who know that, I use Itzekson-Zuber formula, which is very simple for unitary group and quite hard for orthogonal symmetry. So if you, for second correlation function, matrix is 2 by 2, it's not so bad, but if you want to obtain higher correlation, it's much more complicated.
Again, you get the same answer.
No, you have the same answers for GOE. Yes, you have, and the answer is different for GOE. For GOE, you have the derivative of the sign kernel. Yeah.
Back, one slide back.
Yes.
So what is the? Okay, so what is it? What's the definition of F2?
F2 is just two determinant. Is the mean of the two determinant, average of two determinant.
Product of two curves.
Yes, yes, yes.
So you were saying that.
Yes, the second part was done very recently by a transfer matrix approach, and as for me, I feel it's like a more promising approach for 1D case. That's what we can do here. So let me describe the supersymmetric result now for the full model and start for the density of states. So the result in 3D was obtained in 2002, and it was proved in the same model, so with the same covariance, but in 3D case was obtained that if you take the normalized expectation of the trace, so the average density of states, and subtract the Stiglitz transform of semicircle law, then the error will be C of order 1 over W square, and this bound is uniformly is imaginary part, and in W which bigger than, so you can see that we have this for arbitrary short scale, so imaginary part of Z is not important here. All previous results, that was not previous to this one, but all now results about the density of states which we have now, they deals with imaginary part of Z of order 1 over W. Certainly this result is more powerful because they consider not the average density of states, they consider the single elements of the Green's function or density of states without expectation, and from this result one can prove something about delocalization and something like this. But there is no other way except supersymmetry to obtain something on the short scale smaller than 1 over W, and this is very important here.
Make the imaginary part small.
Yes, yes, because here you can put it equal to 0. It's uniform on this. And the second result is work in progress, so we almost finished it, but probably not finished yet. That's why I wrote that it is in progress. We want to obtain the same result for the average density of states in 1D case.
Our result did not work in 1D. So
Yes. Yeah, because
it looks like it should be harder, but you need a different technique.
Yes, so the first result was obtained by cluster expansion, and the technique which very high rely on the Fourier analysis in 3D. For 1D, the Fourier analysis is completely different, so you can't apply the same technique. You have to do something, some different stuff. And here we done this by, again, the supersymmetric transform matrices, which we obtain here. And so this is the result for the density of states, and now let me formulate the result for the full model. So result for full model will be, so all this result is for the model like this, with J of order W square Laplacian plus 1 inverse.
So that result you have this average density?
Yes, certainly, average density, yes. So it's not the local semicircle in Erdős-Yau sense. It's just, yeah, so it's everything here is for the, so this roughly speaking, it's not the local result, so it can't help you to prove delocalization or something like this. This is the result, only it's local, but it's local result about the density, so it's not.
It doesn't tell you anything about eigenvectors.
Eigenvectors, yeah, correlation function, something like this. Gap, yes. Okay, so, and now let me formulate two results about this model, Wigner Gauge-Invariant model, and about the correlation function or localization length. The first result was obtained in 2014 for this kind of matrices, and it was proved that if W of order n, so your band is pretty wide, then you can obtain the second correlation function if n tends to infinity, converge weakly to 1 minus sine kernel square, which is the determinant of sine kernel which we expected to have. And this is in any dimension. It's not important here what kind of dimension we have, because this is because we have very wide band. That's why it's independent on the dimension. And the second result, which was roughly speaking rely on the first one, so combine these techniques with the green function comparison strategy, which comes from Erdős-Yau approach. Erdős and Bau can prove that localization length is bigger than W in 7/6 in a strong sense. So, which means that now they can prove this for the all eigenvectors, not for the most part, but just for the all. And technically, this means that we really can control the absolute value square of the Green's function up to the order of imaginary part 1 over n. But so they can do it for more general case, so they can take non-Gaussian elements, and also they can take a little bit more general covariance, so not like this, but you can take weighted Laplacian here with some conditions, so it's a little bit more general. But let me emphasize that the main part of this work is the work with Gaussian elements, with Grassmann part. All other stuff is just a standard way how to work with these matrices. So they need something to compare with, and this is the main part what you have to obtain here.
So they get this localization like for all.
Yes, this is localization in a strong sense, not strong, with yes.
Not weaker sense that
yes, yes.
And this also basically uses the supersymmetric method that you.
Yes, so roughly speaking, they take the Gaussian case, they write 60 pages how they work with Gaussian case, and then in 5 pages they explain why they can compare it with non-Gaussian elements. This is the paper.
But they're using supersymmetry too.
Yes, yes, they hardly rely on the technique which was developed in first case. Yeah. Okay, so let me now briefly remind what is, for people probably who don't know, what is Grassmann integration and why it's useful here. So we take sets of 2n variables, we generate the Grassmann algebra, they anti-commute with each other, so the elements of this algebra is just polynomial, and we can define any smooth function by substituting, so if chi is such an element, we can substitute in the Taylor series of f chi minus a, and at point Taylor series and point a, and we obtain again some polynomial because we know that chi, since elements are anti-commuting, the square of each variable is 0, so this means that chi minus a to the nth power is always 0, so the series always terminates up to some point. So this is just example, so if we compute the exponent of some psi bar psi, then this is just 1 plus psi b psi by psi. If you take the quadratic form, then we have here just quadratic part plus quartic part, which is, you can see this is the determinant, which will be important now. And now let us define, following Brazen, let us define the formal integral on these variables. Integral of 1 is 0, integral of each variable is 1 over these variables. So again, if we repeat multiple integral is defined to be repeated one, we can extend this definition to all the algebra, and roughly speaking, what our integral does, we take, if we take some polynomial and integrate it over pk and so on pc1, then the integral is the top coefficient near this product. That's all what we have here. But you can see from this example, and simply if you obtain not as a just 2 Grassmann, but some for more general quadratic form, you can simply obtain that if you consider the integral of the exponent, you obtain the determinant. So the controversial part, when you take, instead of psi, you take Gaussian variables, you can obtain that this is determinant inverse, which is usual Gaussian integral. So as I told, we want to take write some integral representation for determinant in the numerator and determinant in the denominator. And this is a part for numerator. For the denominator, we use the standard Gaussian case. If you want to combine two of them, we have to write it like in terms of super matrices, which why it's called supersymmetry, and you have this super in everywhere. So, which means that you now your F is not usual matrix. It consists of 4 blocks, A and B are commuting blocks, so it's complex number plus some products of even number of Grassmann, and sigma and rho are odd Grassmann, so they anti-commute. And our vectors phi has a k component Grassmann component and k complex component. Then combine Gaussian integration with integration over the Grassmann variable, we can write integral. Here integral, certainly one integral is usual complex integral, second integral is Grassmann integral. Then you can write this, and this will be superdeterminant, where superdeterminant can be defined in this way. You can see that if you put formally sigma and rho equal to 0, you obtain just one determinant divided by another one. This is what you have to obtain. Okay, so let me now show you how in
Does the product property hold for superdeterminant?
yes. If I defined it here in a proper way, it should. Yeah, it's in general, it can be that I define it in the wrong way. I usually can. Yeah, but I think that yes. Yeah, I think that's right, probably. Okay.
But anyhow, superdeterminants of A type, supermatrix A times supermatrix B, the determinants do have the right properties.
Okay, so let me show again briefly how it works. So for characteristic polynomials first. If we take, so what is the idea? The idea is to represent the determinant as a Grassmann integral, then take an expectation as a usual Gaussian, because expectation is some Gaussian integral. Now we have exponent with some Gaussian stuff. We can write this exponent, take some elements which are independent, then we cannot take this expectation over elements H. What we have obtained after this? After this, we obtain the following.
Going a little fast, so
Yeah.
So this is the product. You're writing the product.
Yes, this is just the product of two
This
determinants.
is the product of two determinants. You haven't taken any averages yet, but you're going to take it at the next line, or?
Yeah, we want to now. So this is just
Without
product.
the expectation, just the
Yeah. Now.
That's right. That's correct.
Then you take
Then you take
Yes, because now we want to collect the elements near the independent variable. So I want to just take it like a usual Gaussian
So that's not
integral.
an equality sign, but anyhow.
No, it is an equality because I don't
yeah,
have
you
it.
have the expectation.
Yes,
You didn't
yes.
fine.
Yeah. Now this is the usual Gaussian integral. In H, it's a usual Gaussian integral. I can take the expectation over H because you have linear combination. So real part times some form, imaginary part times some form. This is just linear. So roughly speaking, what you have here, you have your measure is some. So what you have trace of H square. And here you have H, some vector H. And you want to take the Gaussian integral here. So this integral in H. Yes, you can do it very simply, and after this you obtain the expression in Grassmann variables. This is expression, so what you have to do, you just have to substitute the measure from the measure J that you have for this matrix that you have here. Now the J is general, so I don't use that it's minus W square Laplacian plus 1. I just use the general J. Now you have expression over the Grassmann variables.
Now the averaging over the randomness is completely
Yes, yes. So
different. You
now,
have all this complicated
Yes.
Grassmann stuff running around.
yes, we have only Grassmann variables. That's all that what we have. So now we want to integrate out the Grassmanns because we want to obtain something without them. So
Let me just say this. If I take if I just wanted to compute the average of a characteristic polynomial product of 17 guys, I could just expand them out.
yes, certainly, but
Switch the sum.
certainly you
the
can,
average,
but
and
this-
that is what's
yes,
happening
but
here in some way, right?
this help you to keep all your combinatoric inside.
You can do
Roughly
that.
speaking, yes, you're completely right. This helps you. Yes.
It'll be formal, but you'll see that there's another step here.
Yes. So what you can do, what you want to do next, you want to integrate out the Grassmanns. You know how to integrate the quadratic form in Grassmanns, but here you have the chaotic terms, as you can see. So you want to somehow avoid this chaotic term, to transform into quadratic one. How you can do this? The standard way how you can do this is a Hubbard-Stratonovich transform, which has a strange name, but still it's just a simple Gaussian integral. It's nothing more. So you apply this quantity that if you take the integral of x squared 2 plus ax, then you obtain e to the a squared over 2. So putting here some auxiliary variables, you can write this integral like this one. So using some auxiliary variables xj, now this xj are complexes. We don't have any Grassmann there. Okay, so after you did this, you obtain now everything is quadratic in psi, and you can take the integral in psi, which
So
is
I think it's an
Grassmann.
important step. Maybe since Zeb's asking some questions about it, so is that transition clear, or it's just algebra?
It's
right?
just algebra.
It's just algebra.
Yes, you only use this one.
This is Gaussian
This,
identities, right?
Right.
Yeah.
That's
that's all. So you don't have anything really hard here. So after this, you can integrate out the Grassmanns, and what you obtain is the following expression. This is expression. So here, roughly speaking, you don't need to use the form of J. I want to use it because I want to show you why this J is so useful for.
The directly which we get, it's essentially, I mean, Grassmannians were used for combinatorics.
Yes, that's all.
Yeah. No saddle point or nothing.
Yeah.
Then
Yes, here it's really so, but if you try to find something for real correlation function, probably we have to use it more clever. So we don't know how to do it now, but so the only way how mathematician can work with this is integrate out the all Grassmanns. This is the only way how we can work with this. But it seems that it's not the right way to work with them, because physicists do it in another way. They use some very, roughly speaking, they use supersymmetry, which is and they do it in much but we don't really know how to do it. So we don't know how to do it rigorously. They use some symmetry which combines together complex variables and the Grassmann variables, and this can really help you a lot. But we don't know how to do it rigorously. So, but for characteristic polynomials, there is no problem. We can integrate out the Grassmann without them. So what we obtain is the following. Here I use this J. And what we have is, so xj is just 2 by 2 Hermitian matrix. We have one matrix for each side of the lattice. And this is, so here it's written for one decay, but certainly you can write it for any dimensional. Just put here not xj minus 1, but xj prime, where j and j prime are neighbors. That's all. That's all difference.
So maybe go back again. Go back for a second. So when you do this, the xj's, each xj is a 2 by 2.
Yes.
Each xj is 2
yes.
by 2 when you do this
So
transformation.
this is because you wanted to have an expectation of a product of two determinants.
Yes.
So you took
Yes.
K as
If
a
you took 2k
prime.
determinants, we have 2k by 2k matrix. Yes, it's right.
If you have,
If you have-
your expression or comment, if you had 3 or 4, you'd have to have your xj's would be.
Yes, yes. 4 by 4 for 4 determinant, and 4 by 4, and so on. Yes, it's true.
Why does J begin at 2?
Because I have Neumann condition. It's not boundary, so it's not periodic boundary condition. I have a Neumann.
They were on the original variables, the Grassmann, but somehow they're now on the x's.
Yes, but this condition. Yes, but this condition should be there. So, okay, and that's what you have. So you have here is like a nearest neighbor interaction, and here you have some external field which goes here. So this picture is more or less familiar for people who work with statistical mechanics. So it looks like.
I just got to remind myself. So again, I see that's the answer, but I want to just go back to the previous slide to see where that comes from.
So this is yes. You have J inverse here. This is transforms to this J inverse is minus Laplacian. You have the Laplacian twice xj square because of this one.
Okay, and what about all this E and C hat stuff?
Frank, you have this one more step here, because here if you just take the determinant, you have to take this xj together with this lambdas. I substitute lambdas that I have. My lambdas now is E plus xi divided by n rho. I substituted here and do the sum. Yes.
Does your lambda appear in there, or where's the lambda?
Not here, but it's here. I have one more variables.
So that's the quadratic part.
Yes, yes. I don't need to do anything with it because I can
You take the quadratic part and you do
yes.
that, and then
integrate together with this quadratic part.
So still all identities.
Yes, yes. It's just
All identities.
yes. It's all identities. There is no something very
Nothing else.
yes. And this is what you really obtain here. And okay, so this is the integral representation for characteristic polynomial. So then, of course, the main point, you obtain the integral representation. The main, now that's all with supersymmetry. You have to analyze it somehow. There can be different technique. Now, I think that probably for this model, the most promising is the transfer matrix approach, and I'll show you why I think so, because let me, so certainly because you have the chain, yes, you have the simple chain, so you have just nearest neighbor interaction, and you can write this as a trace of some operator. nth power of some operator, which is transfer matrix operator. This operator is like this, so you have this Laplacian and multiple from the both sides by some function f, which is half of all that you have here. So your transfer operator is Laplacian, half of this for x, half of this for y or j minus y. And then your integral representation can be written in the following form. You have some constant which depend on w, n, and so on. And you have just trace of this operator that you have here. And so in general, it's quite natural to understand what is the eigenvalues of this operator, how they look like, depending on w, and certainly operators does not depend on n, it depends only on w. So we have to understand the gaps and so on.
So just to make it clear that maybe people who are not so familiar with the transfer matrix, it's just k to the, it's just k composed with itself many times.
Yes.
The big
yeah. So xy is the integral kernel. When you take the nth power, it's integral of all middle terms, and then trace gives you the last integral. So you have the trace of k to the nth power. And what is the main problem? So in general, it's quite classical problem, if you can see, but the main point here is that the operator that you obtain is not self-adjoint because you quadratic part. So let me probably write it a little bit. So what you have here, you can see that it's complex. So you have I near the energy, so it's complex. So it's not, that's why it's not self-adjoint, and so it's not so simple to understand settle really with the perturbation theory in rigorous basis, because you have to work with so it's not completely clear what you need to do with this operator. So certainly it's still compact, so it has eigenvalues. This is okay, but it's not enough to consider just operator plus some perturbation and prove that perturbation is smaller than the gap between eigenvalues, which people usually do with the transfer matrices. Here you have to be more careful with this operator. So from transfer matrix, what probably I have to, from the localization side, what we want to prove. So if we prove, we take the operator k which we have here. If we can prove that the top eigenvalues is of order 1 plus c over w inverse, and the second eigenvalues is of order so if we know that the gap is of order 1 over w squared, then if we, from the localization side, so our n is bigger than w squared, this means that probably I have to say a few words about perturbation here. What is perturbation here? Perturbation here is things which depend on psi. You can see that because all other stuff is just if you put psi equals 0, you obtain some operator which you can analyze. It's still not self-adjoint, but in general you can. So if you put, so your perturbation here is this. So certainly this times this, and you can see that it's of order 1 over n. So if k will be self-adjoint, would be self-adjoint, then if you can prove that the gap of order 1 over w squared and your perturbation is of order 1 over n, then 1 over n is smaller than gap and everything settled. So you have everything you want.
You lost me somehow when you said when you put psi equal to 0, you can analyze.
Certainly, so there is a two problem. First problem is to analyze the main operator with psi equals 0. Certainly you have to analyze it somehow. So this is the main problem. What you want to prove. So what you can, I'll show you. I can't show you the proof because I have probably just for 2 minutes or something like this, but I'm almost over the time. But if you can prove something from it, I just want to show you that it's not enough to prove the gap for this operator, because it's not self-adjoint. You have to obtain something more than gap. You have to some bounds on the resolvent on transfer operator or something like this.
The other work is also not trivial.
Yes,
Okay.
that's what I want to show you. So, and just to give you an idea what is transfer operator here, I want to show, so now let's put xi equals 0. What is the big operator that you have here? It looks like this. It's a product of 3 operators. 2 of them are operators in A and B, so like they looks like this. So it's just harmonic oscillation because f is some function which has 0 and saddle point, first derivative in 0, second derivative is some complex number. So A is some operator which is a harmonic oscillator which is complex constant plus some perturbation, and K is the operator which depends on unitary group and somehow mixed A and B because it depends on variable T which is depend on A and B. So this operator has gap 1 over W, and crossovers happen because of this operator, because this operator has gap 1 over W square. So for the density of states, you don't have this one. You have 2 operators like this, one of this one, and one is very similar to it. And in addition, you have the matrix which comes from Grassmann variables. But still you have to, so that's why in density you don't have any kind of crossover, because you have only operator A which has gaps 1 over W. So this is just a picture to show what you have to deal with. Certainly I have no time to describe what you really can do with this, so let me probably finish at that point.